Hey everyone, hope you're all having a great day. Welcome to Modular Patching 2. In this video we'll be turning the stereo-triggered sampler, a great module from 4MS, into an SD card-backed Varispeed tape player. This patch should also work with the one-channel version of this module that 4MS is coming out with soon. Along the way we'll be learning about full-wave rectifiers and patching our own zero-crossing detector. Without further delay, let's go into a little more detail about the goals for this patch.
Three, two, 1, 10.
As you can
9,
hear, I have the
8,
STS looping a
7,
simple countdown
6,
sample from the factory
5,
bank.
4,
Let's kill the
3,
audio for a bit.
2, 1.
The objective with this patch is to have some signal act as a macro control for tape speed and direction. At 0 volts, the tape will be stalled, while negative and positive voltages will speed the tape up backwards or forwards respectively. I'm going to use the survey knob on the Cold Mac by Whimsical Wraps for my control voltage, but you could use any CV source. We're trying to control sample speed using the distance from 0 on our control voltage, which is exactly what a full wave rectifier does. Conveniently, the Cold Mac has a full wave rectifier on the slope output. If you don't have a full wave rectifier in your rack, I'll show a way to patch up something similar in the next section. I'm going to patch our unaffected control voltage into channel 1 of the Mordax data and an offset version of our rectified control voltage into channel 2. The reason I'm offsetting our rectified voltage is because by default it'll be sweeping from 0 volts to 5 volts, which is going to mean it sweeps from normal playback speed to 5 times faster. I'm offsetting it by negative 2.5 volts so that it instead sweeps from a minimum of 2.5 times slower to a maximum of 2.5 times faster. We can see on the scope that as I turn our Cold Mac knob, which is representing our input control voltage, the blue trace, which is our offset rectified signal, goes down to about negative 2.5 before reflecting up all the way to its highest value. And the same thing happens when we go positive. Here's a patch diagram for where we'll be at once I connect the bias control voltage to the STS's volt per octave input. Now I'm going to turn the audio back on and connect that cable.
5, 4, 3, 2, 1, 10.
We can see that sweeping the Cold Mac survey knob changes the speed just like we want it,
4,
with a low point at 12 o'clock and normal speed around 9:30 and 2:30.
1, 10.
However, the playback
9,
doesn't reverse
8,
when we cross 0
7,
volts.
6,
3, 2, 1.
Okay, I've unpatched everything, and we've got a sine LFO from the spectrum on the Mordax data to more easily visualize this next bit. The reason we need a zero crossing detector for this patch is that the STS's reverse input toggles playback direction when it receives a trigger. If we used something like a comparator on our control voltage, we'd only switch the playback direction when our input control voltage signal goes from negative to positive or from positive to negative, but not both. Here our comparator is set up to output 5 volts when the input is above 0 and 0 volts when the input is below 0. Our comparator output isn't useless though. I've slightly modified this patch so that the comparator output goes from negative 5 to 5 for a larger contrast between the maximum and minimum values. Let's see what happens when we pass it through a high-pass filter to AC couple the signal. Okay, I've hidden the blue trace, which is the amplified comparator output, and I've got data set up to freeze whenever our AC coupled output of the filter goes above half a volt on the red channel. We can see that whenever the sine wave crosses zero, we get alternating spikes from the sharp higher frequency rising and falling edges of our comparator output that the high-pass filter is preserving, while rejecting the static DC voltages of those +5 and -5 volt high and low points of the comparator output. To use this AC coupled signal as a reliable trigger, we'll want to full wave rectify it, so the negative spikes become positive. I don't have another full wave rectifier in my rack, but we can get pretty close by multiplying the signal with itself in a bipolar VCA, or, in other words, 4-quadrant multiplier. I'm going to use the Mutable Instruments blinds. Hiding the red trace and showing the yellow trace, now you can see we have a very usable zero crossing trigger for our patch. If you don't have a comparator, you can use any signal that's discontinuous at 0 volts, like the cold max crease output. You can also patch up a comparator using a quantizer, addressable switch, or most function generators. I'll make our zero crossing trigger pluck the Clouds Parasite's Resonester mode, so we have something to listen to, while some different signal diagrams for patching a zero crossing detector show up on screen. Putting all the pieces back together, I've swapped my sine LFO for the Cold Max survey knob and gotten my playback speed control voltage back. I've also patched our zero crossing trigger signal into the STS's reverse gate input, and we can see that the patch now behaves the way we expect.
Boston. NAC Boston. Philadelphia. WGY Schenectady.
There are a couple small improvements we can make to this patch. First of all, when we pass through 0, reversing the playback direction causes a slight click in the audio. To fix that, I'll use a window comparator, in this case the Jor Analog Compare 2, to output a high gate when our control voltage gets near 0. Then I'll put that gate signal through a slew limiter, so we get a smoother transition on this volume control signal, and finish up by inverting the slewed gate and using that to duct 2 VCAs for the left and right channels of our audio output. Now when we pass through 0 volts and reverse the speed of our tape, we're not getting that clicking. The other improvement I'd like to make is to add a crude wow and flutter simulation. I'll be adding together a couple sine LFOs from Batumi, attenuating them almost all the way for a very subtle effect, and then adding that animation to our playback speed voltage. The modulation should be attenuated until we pretty much can't hear it. Now we're all done with our improvements. Thank you so much for watching this installment of Modular Patching. I've got the finished patch diagram up on the screen right now. If you learned something or enjoyed this video, feel free to like or subscribe. I'll be coming out with more modular tips and tricks in the future. Have a great rest of your day and have fun patching.